Welcome to this quiet corner of the universe, where we can rest together and explore the cosmos with gentle curiosity. I'm so glad you're here tonight, ready to embark on one of the most remarkable journeys imaginable, a voyage that connects you directly to the nuclear heart of our nearest star. Tonight, we'll follow a single photon of light on its epic adventure from the sun's core to your eyes. This isn't just any story about space, this is your story, written in the language of physics and poetry, spanning hundreds of thousands of years in nearly 100 million miles. Every ray of sunlight that has ever warmed your skin began this same incredible journey, carrying with it the memory of nuclear fire and the patient transformation through stellar matter. We'll travel together through this cosmic tale in gentle stages, each one revealing another chapter of how starlight becomes the warmth and light that makes life possible, from the violent beauty of nuclear fusion to the moment when ancient photons finally reach Earth. We'll discover the hidden connections between you and the sun, connections that are both scientifically profound and deeply personal. So settle in comfortably, my friend. Let your breathing slow and prepare to witness one of the universe's most beautiful stories, the journey of sunlight itself. Close your eyes for a moment and imagine the light that's touching your face right now. That gentle warmth, that soft illumination filtering through your window or dancing across your skin. This light carries with it one of the most extraordinary stories in the universe, a tali of Chimi, space, and the incredible journey from the heart of our nearest star to this very moment. The photon that just reached your eye began its epic voyage long before human civilization existed. Before the pyramids were built, before the first cities rose from the earth, before our ancestors learned to harness fire, this single particle of light was already traveling toward you, carrying the promise of this exact instant in time. Think of it as a cosmic letter written in the language of pure energy, addressed specifically to you across the vast distances of space and the even vaster distances of time. Every ray of sunlight is a message from the sun's core, a place so alien and extreme that it exists beyond our everyday understanding, yet so fundamental to our existence that we are quite literally made of its gifts. This is not just any journey we're about to take together. This is perhaps the most important journey in your life, though you've never consciously experienced it. It's happening right now, as it has happened every day since you were born, and as it will continue long after we're gone. Billions upon billions of these messengers of light are arriving at Earth every second, each one carrying the same incredible story. But tonight, we'll follow just one single photon, born in violence and beauty in the nuclear furnace at the sun's heart, destined to travel across nearly 100 million miles of empty space. And finally, after a journey that spans geological ages too, gently touch your retina and become part of your perception, part of your experience, part of you. As you settle into comfort, let your breathing slow and deepen. Feel your body relaxing into whatever surface supports you. In a few moments, we'll shrink down to become smaller than the smallest things you can imagine. And then we'll travel to a place where matter behaves like nothing you've ever seen, where the very atoms dance together in a cosmic ballet that has been playing for 5 billion years. The light touching you now is ancient and eternal, common and miraculous, predictable and mysterious. It connects you to the nuclear heart of our solar system in ways that are both scientifically precise and poetically profound. You are not separate from the sun. You are part of its story, and it is part of yours. Every breath you take, every beat of your heart, every thought passing through your mind in this moment is powered by sunlight that fell on plants, that fed the food chains, that drove the weather systems, that shaped the world into the place where you could exist. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was forged in stars like our sun, scattered across space and gathered again into the planet where you now rest. But for now, let's follow just one photon on its incredible journey. Imagine that we could somehow tag this particular particle of light, mark it as special among the countless trillions that share its fate. Picture it like a glowing ember carried on an invisible wind, or a message in a bottle cast into an ocean of space and time. Our story begins in a place that is simultaneously smaller than a pinpoint and larger than entire continents, hotter than any fire and denser than any metal, a place where time moves differently and matter exists in states that have no names in our everyday language. It begins in the nuclear core of the sun, where temperatures reach 15 million degrees Celsius, and the pressure is so intense that atoms cannot maintain their familiar shapes. Here, in this cosmic forge, our photon is about to be born, not created from nothing, but transformed from matter itself, in a process so elegant and powerful that it has kept our sun shining for billions of years and will continue to do so for billions more. This is where our journey begins, at the moment when matter becomes light, when mass becomes energy, when the fundamental forces of nature perform their most beautiful magic trick. Are you ready to witness the birth of a star's gift to the universe? To follow this messenger of warmth and light as it begins the most epic journey imaginable? Then let's descend together into the heart of the sun, where our story truly begins, in the nuclear fire that makes all life possible. Imagine descending through layers of matter so dense that a teaspoon would weigh as much as a mountain. We're traveling into the sun's core, a sphere roughly the size of Jupiter, nestled at the center of our star like a cosmic pearl hidden within shells of increasingly energetic plasma. Here, in this cathedral of nuclear fire, the temperature soars to 15 million degrees Celsius, hot enough to strip electrons from atoms, leaving behind naked nuclei swimming in a sea of charged particles. The pressure here defies human comprehension. It's 250 billion times greater than the atmospheric pressure you feel right now. If you could somehow stand at this depth within the sun, the weight pressing down on you would be equivalent to having the entire Atlantic Ocean balanced on every square inch of your body. Yet in this impossible environment, something beautiful and essential is happening, the slow, patient process that powers all life in our solar system. In this nuclear forge, hydrogen nuclei simple protons really are being pushed together despite their natural tendency to repel each other. Like trying to force two powerful magnets together at their matching poles, these positively charged particles resist combination with tremendous force, but the sun's core has a secret weapon: overwhelming gravitational pressure that crushes matter until quantum mechanics itself bends to allow the impossible. Picture our hydrogen nuclei as shy dancers at a cosmic ball, circling each other at incredible speeds, approaching and retreating in a quantum waltz that has been playing for billions of years. They're moving at temperatures so high that their velocity becomes a blur of pure kinetic energy. Yet even at these fantastic speeds, they need help to overcome their electrical resistance to each other. This is where quantum tunneling performs this magical phenomenon, so strange that it seems like pure fiction, yet it's happening trillions of times per second in the sun's core. The hydrogen nuclei don't need to completely overcome their electrical barriers. Instead, they can somehow slip through them like ghosts passing through walls. It's as if the universe provides a secret tunnel through the mountain of electromagnetic force, allowing fusion to occur at temperatures far lower than classical physics would predict. When this quantum miracle happens, when the hydrogen nuclei finally embrace the result, is pure transformation. In that instant, matter becomes energy in the most dramatic way possible. One of the protons transforms into a neutron, releasing a positron and a neutrino in the process. The newly formed deuterium nucleus, still glowing with the energy of its creation, immediately seeks out another hydrogen nucleus for a second dance of fusion. This second embrace creates helium-3, and with it, another burst of pure energy. But the dance isn't finished yet. The helium-3 nuclei, each carrying the memory of their nuclear birth, eventually find each other in the crowded ballroom of the core. When they fuse, they create helium-4 and release two protons back into the cosmic dance, completing what scientists call the proton-proton chain, the fundamental process that has kept our sun burning for 4.6 billion years. And in that final moment of fusion, in that instant when helium-4 emerges from the nuclear embrace, our photon is born, not created from nothing, but liberated from the binding energy that once held the original hydrogen nuclei together. It's a gamma-ray photon carrying tremendous energy, vibrating at frequencies so high that they exist beyond the visible spectrum, beyond ultraviolet, beyond X-rays, in a realm of pure electromagnetic force. This newborn photon is unimaginably energetic. It carries thousands of times more energy than the gentle visible light that will eventually reach your eye. If this gamma ray could somehow reach Earth directly, it would be lethal to life as we know it. But the sun, in its ancient wisdom, has built-in systems to transform this raw nuclear fire into the gentle warmth that makes our world habitable. Think of our photon as being born into a cosmic prison, not a malevolent captivity, but a necessary transformation chamber. The core of the sun is so dense with matter that our photon cannot travel more than a few millimeters before it collides with another particle. Each collision absorbs the photon completely and then re-emits it, but not as the same high-energy gamma ray. With each interaction, our photon loses a little energy, its frequency dropping slightly, its wavelength growing longer. This is the beginning of the most patient journey in the solar system. Our photon, born in the violence of nuclear fusion, must now play an elaborate game of cosmic pinball, bouncing from particle to particle, gradually losing energy with each collision, slowly working its way outward through the unimaginably dense matter of the solar interior. The path ahead is not straight, nor is it predictable. Random walks. Scientists call VIMA journey, where each step is determined by chance, where the final destination is certain, but the route is entirely chaotic. Our photon might bounce toward the surface, only to be deflected back toward the center. It might spiral sideways for thousands of years before making any progress outward. It might be absorbed and re-emitted millions of times before it travels a single mile from its birthplace. But patience is encoded into the very fabric of stars. The sun has been performing this transformation for longer than complex life has existed on Earth, and it will continue long after our species has evolved beyond recognition. Each photon that escapes the core carries with it the accumulated time of its journey. Some take thousands of years, others take millions. The light touching you now might have begun its journey when our ancestors were still learning to use tools. As our newborn photon begins its first tentative bounces through the incredible density of the core, it joins a migration that involves trillions upon trillions of its siblings, all moving outward with infinite patience, all carrying the nuclear fire toward the surface where it can finally escape into space. This is how stars breathe, how they slowly exhale the energy created in their hearts. The core where our photon was born contains only about 2% of the sun's total volume, yet it produces virtually all of the star's energy. It's a nuclear reactor perfectly balanced between gravitational collapse and nuclear explosion, maintained in equilibrium by forces so finely tuned that even small changes would either snuff out the fusion fires or cause the star to tear itself apart. But for now, our photon knows nothing of these cosmic balances. It knows only the constant dance of absorption and emission, the gradual climb from the deepest wells of gravity toward the surface of its stellar home. Each collision changes it slightly, moderates its energy, prepares it for the long journey ahead. The photon that was born as a gamma ray will not reach the surface as a gamma ray. That violent nuclear fire will be tamed, step by step, collision by collision, until it becomes something gentler first, X-rays, then ultraviolet. And eventually, if it's fortunate, the visible light that can carry warmth and illumination across the cold depths of space. This is the sun's gift to the universe, the transformation of raw nuclear power into gentle radiance, the conversion of matter into light, the patient alchemy that makes life possible on distant worlds, and our single photon, newly born in the cosmic forge, is about to begin the longest, most patient journey it will ever know, a journey through the body of a star. As our photon begins its outward journey from the nuclear core, it enters what scientists call the radiative zone, a vast spherical shell that extends from the core to about 70% of the sun's radius. If the core was a cosmic pearl, then the radiative zone is the lustrous shell that surrounds it, a region where matter exists in states that blur the line between solid, liquid, and gas, where plasma flows like liquid metal heated to unimaginable temperatures. Here, the density is still enormous, though, not quite as crushing as in the core. Imagine water that's been compressed until it's 8 times denser than gold. then heated until every atom has been stripped of its electrons. This is the strange matter through which our photon must navigate, a substance that exists nowhere naturally on Earth, yet fills the heart of every star in the universe. The temperature here has dropped from the 15 million degrees of the core to a relatively cool 2 million degrees Celsius. Still hot enough to vaporize any known material instantly, yet cool enough that the nuclear fusion has ceased. This is no longer a place of creation, but a place of transportation of vast highway system designed to carry energy from the stellar core toward the surface. But it's a highway unlike any other. Our photon cannot simply travel in a straight line from the center to the edge. Instead, it must navigate through a three-dimensional maze where every path is blocked by matter so dense that light can travel only microscopic distances before being absorbed and Think of it as trying to walk through a forest where every tree stands only a few inches apart, and every step requires you to squeeze between them. Each time our photon encounters an atom in this dense plasma, something fascinating happens. The atom absorbs the photon completely, taking its energy into its own electromagnetic structure. For a brief moment measured in nanoseconds, the photon ceases to exist as a particle of light. Its energy has become part of the atom itself, raising the atom to what physicists call an excited state. But atoms, like people, don't remain excited forever. In a process that seems almost like breathing, the atom releases this energy by emitting a new photon. This new particle of light carries the same energy as the original. A tiny amount has been converted to heat, warming the plasma by an imperceptible degree, and the direction of this new photon. Completely random. Imagine standing in a hall of mirrors where each reflection sends you off in a completely unpredictable direction. Our photon, which began its journey heading outward from the core, might now find itself traveling sideways or even back toward the center. The next collision might send it upward toward one of the sun's poles, and the collision after that might redirect it toward the equator. This is what mathematicians call a random walk, and it's one of the most inefficient forms of transportation imaginable. If our photon could travel in a straight line, it would reach the sun's surface in about 2 seconds, traveling at the speed of light. But forced to zigzag through countless collisions, it might take anywhere from 10,000 to several million years to complete the same journey. To understand just how labyrinthine this journey is, consider that our photon will be absorbed and re-emitted roughly 1 trillion times before it escapes the radiative zone. Each collision changes its direction randomly, so that mapping its path would create a tangled web more complex than any human technology could render. It's like watching a drunk person try to walk home. They know the general direction they need to go, but each step takes them on a seemingly random detour. Yet there's a strange beauty in this chaos. While each individual photon follows an unpredictable path, the collective behavior of trillions of photons creates a steady, reliable flow of energy from the core toward the surface. It's similar to how individual water molecules in a river might tumble chaotically, yet the river itself flows steadily toward the sea. The plasma through which our photon travels is not uniform. Like layers in a cosmic parfait, the radiative zone contains subtle variations in density and temperature. Closer to the core, the matter is denser and hotter. Farther out, it becomes gradually more diffuse and cooler. These variations affect how our photon interacts with the surrounding matter, creating regions where it might move slightly faster or slower in its outward migration. Sometimes, our photon encounters regions where the plasma is slightly more transparentarious, where the atoms are spaced just a little farther apart, allowing light to travel slightly greater distances between collisions. These are like brief moments of clarity in a fog, where a photon can make significant progress toward the surface. But these moments are rare and brief, quickly followed by regions of even greater density that slow its progress. As our photon continues its random walk through this stellar maze, something gradual but profound is happening. With each absorption and re-emission, it loses a tiny amount of energy. The violent gamma ray that was born in the nuclear fire is slowly being tamed, its frequency dropping, its wavelength growing longer. What started as deadly radiation is becoming something gentler, more suitable for the journey through space that lies ahead. Think of it like a wild river being gradually calmed as it flows through a series of pools and rapids. The energy is still there, but it's being moderated, transformed from something that could destroy to something that can nurture. This is one of the sun's most important functions, not just producing energy, but converting it into a form that can support life on distant worlds. The time scales involved in this journey are difficult for human minds to grasp. Our photon, which was born in a nuclear reaction that took mere moments, might spend tens of thousands of years just in this radiative zone. To put this in perspective, the light that warms your face today might have begun its journey through the sun's interior when early. Humans were first developing agriculture when the first cities were rising from the plains of Mesopotamia. During this inconceivably long journey, our photon experiences no passage of time. From its perspective, traveling at the speed of light between collisions, the journey from absorption to re-emission is instantaneous. It's only when it's trapped within the electromagnetic structure of atoms that time, in any sense we might understand it, has meaning. The photon exists in a strange temporal state, simultaneously ancient and immediate, patient and urgent. Meanwhile, on the surface of the sun, and on distant planets like Earth, life continues its relatively rapid pace. Civilizations rise and fall, species evolve and go extinct, continents drift and mountains form, all while our photon continues its patient random walk through the solar interior. It's a powerful reminder of the different time scales on which the universe operates, the quick heartbeat of life, the slow breath of stars. As our photon gradually works its way outward through the radiative zone, it's participating in one of nature's most elegant processes. The seemingly random collisions aren't really random at all. They're following the fundamental laws of thermodynamics, creating a natural flow of heat from the hot core toward the cooler surface. Each absorption and emission is like a tiny heat pump, moving thermal energy outward, ensuring that the sun can continue to shine steadily for billions of years. The plasma itself is flowing, too, but so slowly that the movement is barely perceptible. Unlike the turbulent convection that occurs in the sun's outer layers, the radiative zone is relatively calm. The matter moves in slow, stately currents, carrying some of the heat outward through simple conduction, while the bulk of the energy travels in the form of radiation photons like ours, all playing their part in the cosmic pinball game. Our photon has now been traveling for perhaps 50,000 years. Though it has moved only partway through the radiative zone, it has been transformed from a deadly gamma ray into something more like an X-ray, still dangerous to life, but much gentler than when it began. Its energy has been gradually dissipated through countless interactions, yet it still carries the essential message of its nuclear birth, the gift of fusion energy, slowly making its way toward the surface. The journey ahead is still long, and the destination of the sun's visible surface remains distant. But our photon continues its patient migration, one random collision at a time, gradually climbing out of the gravitational well of the solar core, slowly moving toward the regions where matter becomes thin enough for light to finally escape into space. This is the hidden part of sunshine, the incredibly long, patient journey that every ray of light must complete before it can begin its brief sprint across the solar system. Our photon carries within its electromagnetic field the accumulated time of this journey, the memory of countless collisions, the gradual transformation from raw nuclear fire into something approaching the gentle radiance that makes life possible. After hundreds of thousands of years of random wandering through the radiative zone, our photon finally reaches a boundary that changes everything. At roughly 70% of the sun's radius from the center, the nature of the solar interior transforms dramatically. The temperature has dropped to about 2 million degrees Celsius. And something remarkable happens. The plasma becomes opaque enough that radiation alone can no longer efficiently transport heat outward. This is where a photon's journey takes on an entirely different character. Welcome to the convective zone, a turbulent ocean of plasma that extends from this invisible boundary all the way to the sun's visible surface. Here, the orderly random walk of the radiative zone gives way to something much more dynamic and chaotic. Massive convective currents that rise and fall like slow-motion tsunamis made of superheated gas. Imagine the largest pot of boiling water you can conceive of now, multiply that by a trillion, heated to temperatures that would vaporize planets, and set the entire system in motion with the energy output of 1 million nuclear power plants every second. This is the convective zone, where hot plasma rises from the depths, while cooler plasma sinks back down, creating circulation patterns so vast that individual cells can be larger than entire planets. Our photon, which has spent geological ages bouncing randomly from particle to particle, now finds itself caught up in one of these ascending currents. Think of it as finally catching a ride on a cosmic escalator after walking up countless flights of stairs. The plasma carrying our photon is buoyant heated by the energy rising from below. It's less dense than the surrounding material, and it begins to rise toward the surface like a bubble in champagne. But this is no ordinary bubble. The convective cell our photon is joined might be 1,000 kilometers across, large enough to swallow Earth several times over. It rises through the solar interior at speeds of about 1 meter per second, which might seem slow. But remember that our photon has been making almost no net progress for hundreds of millennia. Now, suddenly, it's ascending steadily toward the surface at a pace that, while still requiring centuries to complete, represents dramatic progress compared to its previous random wandering. The physics of this convective transport is elegantly simple, yet the reality is breathtakingly complex. Hot plasma rises because it's less dense than its surroundings, carrying enormous amounts of thermal energy upward. As it rises, it gradually cools, becoming denser, until it eventually sinks back down to be heated again and begin another cycle. It's the same process that drives weather on Earth, but operating under conditions so extreme that matter behaves in ways that seem almost magical. Our photon continues to be absorbed and re-emitted countless times during this journey. But now these interactions are happening within a mass of plasma that's moving steadily upward. It's like being passed from hand to hand in a crowd that's all walking in the same direction to individual steps. Might still be random, but the overall motion has a clear purpose and destination. The convective currents are not smooth or uniform. They're turbulent, chaotic, filled with eddies and whirls and sudden changes of direction. Smaller convective cells form within larger ones, creating a hierarchy of circulation patterns that extends across multiple scales. Our photon might find itself carried upward for months or years, only to be caught in a downdraft that carries it back toward the radiative zone, where it must wait to catch another rising current. These convective motions create something like weather inside the sun. There are plasma storms larger than Jupiter, currents that twist and spiral in three-dimensional heat, and boundary regions where ascending and descending flows meet and create turbulent mixing zones. The magnetic field of the sun gets twisted and tangled by these motions, eventually emerging at the surface as sunspots, solar flares, and the gorgeous auroral displays that sometimes grace Earth's polar skies. As our photon rides these massive convective currents, it's gradually cooling not because it's losing energy, but because the environment around it is cooling as it moves away from the heat source in the core. The plasma temperature drops from 2 million degrees at the bottom of the convective zone to about 6,000 degrees at the top. This cooling has a profound effect on our photon's ongoing transformation. By now, a photon has been reduced from a gamma ray through X-rays to something approaching ultraviolet radiation. The countless collisions and re-emissions have gradually reduced its energy, stretching its wavelength, taming its violent nuclear birth into something that's beginning to resemble the light that can cross space safely and perhaps even support life on distant worlds. The convective zone is also where the sun begins to rotate differentially, a phenomenon that will become crucial to our photon's final escape. The plasma near the sun's equator rotates faster than the plasma near the poles, creating a shearing motion that twists magnetic field lines and stores enormous amounts of energy. This differential rotation is what drives the solar dynamo, the process that creates and maintains the sun's magnetic field and influences everything from sunspot cycles to the solar wind. Our photon, carried by these rotating currents, begins to participate in this cosmic dance. Its path becomes influenced not just by the upward convective flow, but by the sun's rotation, creating spiral trajectories that add even more complexity to its journey. It's like riding a carousel that's also an elevator, moving both upward and around as it approaches the surface. The timescales in the convective zone are dramatically different from those in the radiative zone, where a photon might have spent hundreds of thousands of years making relatively little progress through the random walk below. It can now traverse the entire convective zone in perhaps a few hundred years. This is still an enormous span of time, by human standards longer than recorded history, but it represents a dramatic acceleration in the photon's journey toward freedom. As our photon rises through this plasma ocean, it encounters regions where the convective currents become more organized and powerful. Near the top of the convective zone, the rising plasma begins to cool rapidly as it approaches the point where it will finally be able to radiate energy directly into space. This creates a kind of traffic jam of thermal energy, with hot plasma constantly arriving from below while the cooler plasma above struggles to radiate its heat away. The boundary between the convective zone and the sun's surface is not sharp or well. Instead, there's a gradual transition region where convective transport slowly gives way to radiative cooling. Our photon, after its incredibly long journey through the solar interior, is finally approaching the moment when it can escape the gravitational embrace of the sun and begin its sprint across the solar system. But even as our photon approaches this momentous transition, it continues to be transformed by its interactions with the surrounding plasma. The violent gamma ray born in nuclear fusion has now been tamed into something much gentler, perhaps ultraviolet radiation, or even visible light. The exact energy it carries depends on the countless random interactions it has experienced. But one thing is certain: it has been fundamentally changed by its passage through the sun. The convective currents that have carried our photon upward are also carrying something else: the magnetic field lines that thread through the solar plasma like invisible highways. These magnetic structures, twisted and tangled by the convective motions, will play a crucial role in determining exactly how our photon escapes the sun and what path it takes into space. Our photon has now traveled from the incredible density and temperature of the nuclear core, through the patient labyrinth of the radiative zone, and up through the turbulent ocean of the convective zone. It has been transformed from deadly radiation into something approaching the gentle light that makes life possible. And it's finally approaching the boundary where it can escape the sun's gravitational well and begin its journey across space. The surface of the sun, the photosphere, as astronomers call it, is now just a few hundred kilometers away. For our photon, which has traveled hundreds of thousands of kilometers from the core and spent hundreds of thousands of years making the journey. This final approach represents both the end of one epic voyage and the beginning of another equally remarkable adventure. As our photon approaches the sun's surface, riding the final currents of rising plasma, it enters a region unlike anywhere else in the solar system. This is the photosphere, literally the sphere of light, a relatively thin layer only about 500 kilometers deep, where the sun transitions from being opaque to transparent. Here, after hundreds of thousands of years trapped within the solar interior, photons like ours finally gain the freedom to escape into space. The photosphere is what we see when we look at the sun through proper solar filters. It appears as a bright, yellow-white surface, but it's not a surface in the way we normally think of one. There's no solid boundary here, no sharp edge where gas ends and space begins. Instead, the photosphere is more like the visible edge of fog or region where the solar atmosphere finally becomes thin enough for light to travel freely, where the countless collisions that have defined our photon's journey finally come to an end. The temperature here has dropped to about 5,800 degrees Celsius, still hot enough to vaporize any known material, yet dramatically cooler than the millions of degrees our photon experienced in its birth. This cooling has a profound effect on the nature of matter in the photosphere. For the first time since leaving the core, atoms begin to recapture some of their electrons, creating partially ionized gases that interact with light in complex and beautiful ways. Our photon, now transformed through its long journey from a deadly gamma ray into visible light, perhaps glowing with a warm yellow color, we associate with sunshine, finds itself in a region where its final destiny will be determined. The photosphere is dynamic and ever-changing, covered with granulation patterns that look like slowly boiling rice when viewed through telescopes. Each granule represents the top of a convective cell, a place where hot plasma wells up from below, spreads outward, and then cools and sinks back down. These granules are enormous by terrestrial standards each, one larger than Texas, yet small enough that thousands of them can fit across the sun's face. They constantly appear and disappear, lasting only about 10 minutes each as the convective process that creates them continuously evolves. Our photon might escape from the bright center of a granule where hot plasma is rising and radiating intense light, or from the darker intergranular lanes where a cooler plasma is descending. The exact wavelength and energy of our photon at the moment of escape depends on which atoms it last interacted with. Hydrogen atoms in the photosphere absorb and emit light at very specific wavelengths, creating the characteristic yellow glow we associate with sunlight. Helium, carbon, oxygen, iron, and dozens of other elements each add their own signature wavelengths to the solar spectrum, creating a complex rainbow of colors that tells the story of stellar nucleosynthesis and atmospheric chemistry. But our photon faces one final challenge before it can truly escape the sun's magnetic field. The convective motions that carried our photon to the surface have also twisted and concentrated magnetic field lines into complex patterns. In some regions, these magnetic structures emerge from the photosphere as dark sunspot areas, where the magnetic field is so strong that it suppresses convection and creates cooler, darker regions on the solar surface. In other areas, magnetic field lines arch high above the photosphere, creating invisible highways that channel solar plasma into space. Sometimes these magnetic structures become unstable, snapping and reconnecting in violent events called solar flares that can release more energy in minutes than human civilization uses in years. But for our photon, the magnetic field represents something different, to a final filter that influences the direction and polarization of light as it escapes the sun. The moment of escape itself is both dramatic and anticlimactic. After hundreds of thousands of years of constant interaction with matter, our photon suddenly finds itself in a region where the plasma density has dropped low enough that it can travel significant distances without being absorbed. The transition happens over just a few hundred kilometers, a tiny distance compared to the vast journey it has already completed. One moment, our photon is still bouncing from atom to atom, still trapped in the endless dance of absorption and re-emission that has defined its entire existence. The next moment, it breaks free from the last wisps of solar atmosphere and streams outward into space at the speed of light, carrying with it the accumulated energy of nuclear fusion and the memory of its incredible journey through the body of a star. The direction of its escape is influenced by the granulation patterns on the solar surface. If our photon emerges from the bright center of a granule, it carries slightly more energy and streams outward perpendicular to the surface. If it escapes from the edge of a granule or from the darker intergranular lanes, its path might be slightly angled and its energy slightly reduced. The sun's rotation also imparts a subtle influence. Light escaping from the eastern limb of the sun is slightly blue shifted due to the rotational motion, while light from the western limb is slightly red. Our photon carries within its frequency the signature of the sun's 25-day rotation period. Though this effect is so small that it requires sensitive instruments to detect, as our photon finally breaks free from the gravitational embrace of the photosphere, it experiences something it has never known before: unimpeded travel through space. For the first time since its nuclear birth, it can travel in a straight line at the speed of light, no longer subject to the constant collisions and random redirections that characterize its journey through the solar interior. The escape itself marks a fundamental transformation in our photon's existence. Inside the sun, it was constantly interacting with matter, constantly being absorbed and re-emitted, its identity fluid and changeable. Now, streaming through the vacuum of space, it becomes fixed and permanent. Its wavelength, energy, and direction of travel are now set until it encounters matter again. Behind it, the photosphere continues its eternal dance of granulation and magnetic activity. New photons are escaping every instant, trillions upon trillions of them, each carrying their own story of nuclear birth and slow migration through the solar interior. Some escape from regions of intense magnetic activity, others from quiet areas where convection proceeds unimpeded. Together, they create this steady, reliable light that has warmed the solar system for billions of years. Our photon now joins this cosmic river of light streaming outward from the sun in all directions. It carries within its electromagnetic field the energy that was once locked in the nuclear bonds of hydrogen atoms. Energy that has been patiently transported across hundreds of thousands of years and hundreds of thousands of kilometers to reach this moment of liberation. The sun shrinks behind it not because the sun is moving, but because our photon is traveling away at 300,000 kilometers per second, covering distances that would take human spacecraft years to traverse in mere seconds. The solar system opens up ahead of it, a vast expanse of mostly empty space punctuated by the gravitational islands of planets, moons, asteroids, and comets. But our photon's journey is far from over. It has completed the first and longest phase of its epic voyage. But now it faces a different kind of journey. 8 minutes and 20 seconds of travel through the cold vacuum of interplanetary space, carrying its precious cargo of solar energy toward whatever awaits it in the outer solar system. The photosphere, source of its freedom, gradually fades behind it. Our photon has escaped the sun, but it carries with it the essence of stellar fire, the gift of fusion energy that will soon warm distant worlds, and perhaps, in ways it could never predict, become part of the story of life itself. Now our photon experiences something unprecedented in its long existence, the profound silence and emptiness of space. After hundreds of thousands of years of constant interaction with matter, of being absorbed and re-emitted trillions of times, it now travels through a vacuum so complete that it might not encounter another particle for minutes or even hours. This is freedom on a cosmic scale, the ability to travel in a perfectly straight line at the maximum speed the universe allows. At 299,792,458 meters per second, the speed of light, our photon begins its sprint across the solar system. This phase of its journey, which will last just 8 minutes and 20 seconds, covers a distance of nearly 150 million kilometers. To put this in perspective, our photon will travel farther in these few minutes than all of human history's space missions combined. Farther than light travels in a year around Earth's orbit. The first few seconds of this journey take our photon through the sun's extended atmosphere, the corona, chromosphere, and solar wind. These outer layers of the sun are incredibly tenuous compared to the dense plasma our photon has left behind, yet they're still far more substantial than the interplanetary medium it will soon encounter. The corona, visible during solar eclipses as a ghostly white halo around the sun, extends millions of kilometers into space. Temperatures paradoxically rise against from the 5,800 degrees of the photosphere to over 1,000,000 degrees in the corona. This heating is driven by magnetic reconnection events and wave interactions that scientists are still working to understand. Our photon passes through this superheated but incredibly thin plasma in seconds, barely interacting with the sparse particles it encounters. As our photon continues outward, it enters the solar wind, a constant stream of charged particles flowing away from the sun at speeds of 300 to 700 kilometers per second. This might seem fast, but our photon, traveling at the speed of light, overtakes even the fastest solar wind particles as if they were standing still. The solar wind creates a kind of weather in space, carrying magnetic fields and energetic particles throughout the solar system. But for our photon, it's just another mostly empty region to travel. The space between the sun and Earth seems empty to our everyday experience, but it's actually filled with a complex ecosystem of electromagnetic fields, particle streams, and gravitational influences. Our photon passes through regions where the solar wind interacts with planetary magnetism, where cosmic rays from distant stars streak through the solar system, and where the magnetic field lines from the sun stretch and twist in complex patterns. About 2 minutes into its journey, our photon passes through the orbit of Mercury, the innermost planet. If Mercury happens to be in the right position, our photon might graze its thin atmosphere or strike its cratered surface, but the chances of this are astronomically small. The solar system is mostly empty space, and even something as large as a planet occupies only a tiny fraction of its orbital path. Mercury, when our photon glimpses it, is a world of extremes baked to 430 degrees Celsius on its day side, frozen to minus 170 degrees on its night side. Any photons that do reach Mercury's surface are either absorbed, heating the rocky regolith, or reflected back into space as infrared radiation. But our photon continues unimpeded, carrying its cargo of visible light deeper into the solar system. At about 3.5 minutes into its journey, our photon crosses the orbit of Venus, Earth's hellish twin. Venus is shrouded in dense clouds of sulfuric acid that create a runaway greenhouse effect, trapping heat until the surface temperature reaches 460 degrees Celsius, hot enough to melt lead. The planet's thick atmosphere would quickly absorb our photon if they met, but Venus, like all the planets, is just a tiny target in the vast expanse of its orbit. Our photon now enters the region of space where liquid water can exist on planetary surfaces, the habitable zone, or as astronomers poetically call it, the Goldilocks zone. This is the narrow band around the sun where temperatures are just right for water to remain liquid, where ice can melt and vapor can condense, where the complex chemistry of life becomes possible. As our photon continues its outward journey, it carries with it exactly the right amount of energy to warm a world in this zone. Too much energy and water would boil away into space. Too little and everything would freeze solid. But our photon, moderated by its long journey through the sun's interior, tamed from deadly gamma radiation into gentle visible light, carries precisely the energy needed to support life. The space our photon travels through is crossed by the orbits of countless astrodrachi debris left over from the formation of the solar system. Most of these are tiny, no larger than mountains or cities, but they collectively represent a vast archive of primordial material. If our photon were to strike one of these asteroids, it would add its tiny contribution to heating the rock, perhaps sublimating ice or causing subtle chemical reactions in surface minerals. But the most likely target for our photon lies ahead, a blue-white marble suspended in the cosmic dark. The third planet from the sun, Earth hangs in space like a jewel against the black velvet of the universe, its white clouds swirling over brown continents and blue oceans, its thin atmosphere glowing with the light of countless photons like our own. Earth intercepts only about 1/2 billionth of the total light output from the sun. Yet this tiny fraction is enough to power all of the planet's weather system, drive photosynthesis in every plant, and maintain the complex web of life that has evolved over billions of years. Our single photon is part of this vast energy budget, carrying its infinitesimal but essential contribution to the continuation of life on Earth. As our photon approaches Earth's orbit, it's still traveling in the same straight line it established when it escaped the sun's photosphere. It knows nothing of its destination, carries no intention or purpose beyond the fundamental properties encoded in its electromagnetic field. Yet it's approaching a world where its arrival might trigger a cascade of events absorbed by a leaf to power. Photosynthesis, striking a solar panel to generate electricity, or perhaps, in the most poetic outcome of all, entering a human eye to create the sensation of vision. The journey across the solar system has taken our photon through regions where space-time itself is subtly curved by the sun's gravity, where the very fabric of reality is warped by the presence of massive objects. These gravitational effects are tiny, but measurable light rays are bent by about 1.75 arcseconds as they pass close to the sun's limb, an effect that was used to confirm Einstein's theory of general relativity during a solar eclipse in 1919. Our photon also carries with it information about the sun's surface and interior. Its wavelength encodes details about the temperature and chemical composition of the photosphere where it originated. Its polarization carries information about magnetic fields, even its precise timing when it was emitted compared to other photons, a story about the complex dynamics of the solar atmosphere. As our photon covers the final millions of kilometers of its journey toward Earth, it passes through increasingly complex regions of space. Earth's magnetic field extends far beyond the planet itself, creating a magnetosphere that deflects charged particles and creates the beautiful auroras at the poles. But our photon, carrying no electric charge, passes through this magnetic barrier as if it weren't there. 8 minutes and 20 seconds after leaving the sun's surface after a journey of 149,597,870 kilometers through the vacuum of space, our photon approaches Earth's atmosphere. Behind it stretches an invisible line connecting this moment to the nuclear fire at the sun's core. a path that represents one of the most fundamental energy transport processes in the universe. The blue glow of Earth's atmosphere appears ahead, thin as an eggshell, but crucial to the story that's about to unfold. Our photon is about to encounter matter again for the first time since escaping the sun, and this encounter will determine its ultimate fate in the grand story of stellar energy reaching a living world. As our photon approaches Earth at the speed of light, it encounters the planet's atmosphere, a delicate envelope of gases that extends hundreds of kilometers above the surface, gradually thinning until it merges with the vacuum of space. This atmospheric boundary isn't sharp like the edge of a solid object, but rather a gradual transition from the emptiness our photon has traveled through to the increasingly dense mixture of nitrogen, oxygen, and trace gases that make life on Earth possible. The first molecules our photon encounters are in the exosphere, the outermost layer of Earth's atmosphere. Here, at altitudes above 700 kilometers, the air is so thin that molecules rarely collide with each other. They follow ballistic trajectories more like satellites than gas particles, and some escape entirely into space. Our photon passes through this tenuous region with barely any interaction, perhaps scattering off an occasional hydrogen or helium atom, but continuing essentially unimpeded toward the denser layers below. As it descends through the thermosphere, our photon begins to encounter more atmospheric particles. The air here is heated by the absorption of high-energy solar radiation, X-rays and ultraviolet light that are harmful to life but are absorbed by the atmosphere before they can reach the surface. The temperature can reach over 1,500 degrees Celsius, but the air is so thin that there's almost no heat to transfer. Our photon, carrying visible light rather than dangerous radiation, passes through this protective layer with minimal interaction. The mesosphere, Earth's middle atmospheric layer, is where a photon first begins to experience significant scattering. Here, between 50 and 85 kilometers above Earth's surface, the air is still incredibly thin by surface standards, but dense enough to interact with light in measurable ways. Molecules of nitrogen and oxygen begin to scatter some of our photon's electromagnetic field, a process that contributes to the blue color of the sky seen from below. But it's in the stratosphere where our photon encounters one of Earth's most crucial atmospheric components, ozone. These three-atom oxygen molecules, concentrated in a thin layer between 15 and 35 kilometers above the surface, absorb ultraviolet radiation that would otherwise sterilize Earth's surface. Our photon, carrying visible light, passes through the ozone layer without being absorbed. But it's traveling alongside countless ultraviolet photons that are being captured and converted to heat, warming the stratosphere and creating the thermal inversion that defines this atmospheric layer. As our photon continues its descent, it enters the troposphere, the lowest and dense layer of Earth's atmosphere, where all weather occurs and where most of the atmosphere's mass is concentrated. Here, the air pressure and density rise dramatically, and our photon begins to experience significant interactions with atmospheric molecules. The process that affects our photon most strongly is called Rayleigh scattering, named after the British physicist Lord Rayleigh, who first explained why the sky appears blue. As our photon encounters molecules of nitrogen and oxygen that are much smaller than its wavelength, it has a probability of being scattered in a random direction. The probability of this scattering depends strongly on the photon's wavelength. Blue light is scattered much more strongly than red light. If our photon happens to carry blue wavelengths, it might be scattered multiple times as it passes through the atmosphere, bouncing from molecule to molecule in a process reminiscent of its journey through the sun's interior, though much faster and less systematic. This scattering is what creates the blue dome of sky we see during the day's sunlight, scattered in all directions by atmospheric molecules. But let's imagine a photon has managed to avoid major scattering events and continues relatively directly toward Earth's surface. As it descends through the troposphere, it encounters increasingly complex atmospheric phenomena. It passes through regions where water vapor condenses into clouds, where tiny droplets and ice crystals can scatter and absorb light. If our photon encounters a cloud, it might be scattered multiple times within the water droplets, emerging in a random direction, or it might be absorbed entirely, its energy converted to heat that helps drive the planet's weather systems. The atmosphere our photon travels through is dynamic and ever-changing. It contains dust from distant deserts, salt crystals from evaporating seawater, pollen from plants, smoke from fires, and countless other particles that can interact with light. Each of these encounters has the potential to change our photon's path or absorb its energy entirely. If our photon survives its passage through the atmosphere without being absorbed or scattered away from its original path, it finally approaches Earth's surface after a journey that began in nuclear fire and has traversed the solar system. The surface it encounters might be ocean, land, forest, or city, each representing a different possible fate for the energy it carries. Should our photon strike the ocean, it might penetrate several meters into the water before being absorbed. It's energy warming, the vast thermal reservoir that helps regulate Earth's climate. Ocean water is remarkably transparent to visible light, and our photon could travel significant distances underwater before finally being absorbed by a molecule of water or encountering a microscopic marine organism. If it strikes land, our photon might be absorbed by soil, rock, or vegetation. Dark surfaces absorb most of the light that strikes them, converting the photon's energy directly into heat. Light-colored surfaces reflect much of the incoming light, sending our photon bouncing back toward space, though usually at longer wavelengths infrared radiation that carries heat rather than light. But perhaps the most remarkable fate awaits our photon if it encounters a green plant. Here, it might be absorbed by a molecule of chlorophyll in a process that has been running continuously for billions of years: photosynthesis, the biological process that converts solar energy into chemical energy, making virtually all life on Earth possible. In the leaf of a plant, our photon's energy would be captured by the complex molecular machinery of photosynthesis, used to split water molecules and combine carbon dioxide into sugars. The oxygen we breathe is a waste product of this process, and the food that sustains all animal life ultimately derives from the solar energy captured by photosynthesis. Our photon, born in nuclear fusion, would finally complete its journey by becoming part of the biological energy cycle that powers life on Earth. Or perhaps our photon has an even more poetic destiny. Maybe it will enter a human eye, striking the retina, where specialized cells called photoreceptors will absorb its energy and convert it into electrical signals. These signals will travel through the optic nerve to the brain, where they will be processed into the sensation of vision, the perception of light, color, and form that allows us to see and understand our world. In this moment, our photon born in the nuclear fire of the sun's core, aged through hundreds of thousands of years of random walks through stellar plasma, cooled and moderated by countless collisions, freed to race across the solar system at the speed of light, and finally delivered to Earth, would become part of human consciousness itself. Part of the sensory experience that connects us to the universe around us. This is the ultimate transformation, from nuclear energy to biological perception, from stellar fire to human awareness, from the heart of the sun to the moment of seeing. Our photon's incredible journey would end not in darkness, but in the light of understanding. And so we return to where we began, to you, here in this moment, with sunlight touching your skin or filtering through your window. But now you know the secret that light carries. Every ray of sunshine is a messenger from the deep past, a traveler from the nuclear heart of our star, carrying with it the story of one of the universe's most fundamental processes. The light reaching you now has completed a journey that spans not just space, but time itself. It carries within its electromagnetic field the accumulated history of its passage through. The sun dissipation ran the walk through plasma denser than gold, the slow ascent through convective currents larger than planets, the final escape through the turbulent photosphere, and the swift sprint across the void between worlds. Think for a moment about the incredible chain of events that had to unfold perfectly for this light to reach you. The nuclear fusion in the sun's core had to maintain its delicate balance between gravitational collapse and explosive expansion. The convective currents had to carry energy upward through layers of plasma heated to millions of degrees. The sun's magnetic field had to allow the light to escape without trapping it in coronal loops or redirecting it away from Earth. The Earth had to be in precisely the right position in its orbit. Our planet's atmosphere had to be transparent enough to allow the light through while opaque enough to protect us from harmful radiation. and countless random scatterings and absorptions had to avoid diverting this particular photon away from its ultimate destination. When you feel the warmth of sunlight on your face, you're experiencing the culmination of processes that began hundreds of thousands of years ago in temperatures and pressures that exist nowhere else in the solar system. You're feeling the gentle touch of nuclear fire, tamed and moderated by its long journey through stellar matter, delivered across the vast distances of space at exactly the right intensity to warm your skin without harming you. Every plant that grows, every breath you take, every beat of your heart is powered by this same process. The food you eat captures sunlight through photosynthesis. The weather that shapes our planet is driven by solar energy heating the atmosphere and oceans. Even fossil fuels are ancient sunlight, stored in the chemical bonds of organisms that lived millions of years ago. You are not separate from the sun. You are part of its story, and it is part of yours. The calcium in your bones, the iron in your blood, the oxygen you breathe were all forged in the nuclear furnaces of stars like our sun and scattered across space when those stars died. In a very real sense, you are made of starlight, animated by starlight, conscious because of starlight. This connection runs deeper than poetry. It's written into the fundamental physics of our universe. The same nuclear processes that power the sun also created most of the elements in your body. The same electromagnetic forces that allow photons to travel across space also enable the chemical bonds that hold your molecules together. The same quantum mechanics that governs fusion in stellar cores also determines how light interacts with the rhodopsin in your eyes, allowing you to see. As you rest now, perhaps ready for sleep, remember that the sun continues its ancient work. Even in darkness, the nuclei fires burn on, creating new photons that will begin their own epic journeys through the solar interior. Some are already on their way, working their patient way outward through the radiative zone, destined to reach Earth decades or centuries from now, carrying the gift of fusion energy to future generations. The universe is vast and often seems cold and empty, but the journey of sunlight reminds us that we live in a cosmos where energy flows from star to star, where nuclear fire can become gentle warmth, where the fundamental forces of nature conspire to create not just planets and galaxies, but the possibility of life, consciousness, and wonder. Sleep peacefully, knowing that you are cradled in the light of the sun, connected by invisible threads of energy and history to the nuclear heart of our nearest star. Tomorrow, new messengers of light will complete their ancient journey to warm your world, each one carrying the same incredible story, each one a gift from the cosmic fire that makes all things possible. The journey of sunlight continues, as it has for billions of years, as it will for billions more, connecting star to planet, energy to life, the nuclear past to the living present, in the endless dance of light across the cosmos. If you enjoyed this journey through the cosmos, consider subscribing for more space sleep stories that explore the hidden connections between you and the universe. Sweet dreams, and may your rest be filled with the gentle light of distant stars.